All right, so we're going to draw some more structures today. We're adding in multiple bonds, so anything could be a single, double, or triple bond. You still work off that same process. So carbon dioxide, we have to know that carbon, it's a C because it doesn't say mon for that first guy. And di means two, so O2. Okay, and I'm going to draw the Lewis structures. Carbon has 4 valence electrons because he's group 14. And oxygen has 6 valence electrons because he's group 16. And now I look and determine the central atom. Well, carbon has 1, 2, 3, 4 gaps, and oxygen has 1, 2. So that means carbon has to be our central atom, which happens quite frequently, actually. Okay, so I'm going to redraw him here with the dots. And 2 oxygens. So I need to spread my oxygens around. And I'm just going to use X's for these guys. And if there's 2, I tend to just put the 2, 1 on either side. But you could put it up or down. It doesn't matter. Just typically people try to stay right on those lines of the page. Okay, and now I know they're at least going to be single bonding, so I'm going to start by making my single bond ovals. And remember, you can grab from anywhere. It doesn't matter, because we'll just rearrange those electrons later so they have pairs. So some people would want to stop here because look, they're bonded. So this is a molecule, right? They're bonded. I didn't change any valence electrons, so I'm good there. But this doesn't meet the octet rule. If I count up 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7. They are not into that full octet rule yet. We got to try to get to 8, unless it's hydrogen or boron. We got to get to 8. So that means I can make a double bond. So I'm just going to pull in another set of electrons. Okay, 1 from the central atom, 1 from the outer one for each one. Okay, so now when I look at carbon, carbon has used up all of his gaps, so he can't do a triple bond in this case because he's doing 2 double bonds. Carbon has 4 gaps, so he has a maximum of 4 bonds. Okay, oxygen has 2 gaps, so has a maximum of 2 bonds or 1 double bond. Okay, and so in this case, oxygen's at its max and carbon is also at its max. So I'm feeling pretty good that I'm probably right, but I'm going to go back and still check again. Valence numbers 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. Okay, so I didn't magically squeeze an extra electron in. Yes, that happens a lot of times. Some people just add an electron because that makes something easier. It might make it easier, but then your answer is not going to come out in the end. Okay, and now let me check to make sure the octet rule worked. 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. Okay, so they all met the octet rule. So now this was my process, so now I'm going to rewrite. I'm going to put my carbon in the center, oxygens on either side. Carbon to this oxygen is a double bond. Carbon to this oxygen is a double bond. What do I have left? 1, 2, 3, 4. Okay, and you always keep the pairs together. Okay, 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Make sure you're going back and showing those unbonded electron pairs because they're going to come into play in the next class. Now, I wouldn't say carbon has a quadruple bond with oxygen because it doesn't. Carbon has 2 double bonds with the 2 oxygens. Okay, so be very careful on your descriptors. Okay, a quadruple bond would be if all 4 bonds would be between carbon and that oxygen, which is not possible, right? Because oxygen could just have 2. All right, our next guy, C2H4. Ah, this guy's weird. I have carbon and I have hydrogen. So what's my central atom? Well, in this case, the carbons are going to share that central position. So you still are doing the same thing. They're just in a sharing rule. And then we have 4 hydrogens. Okay, so I'm just going to put my 4 hydrogens around the 2 carbons. Don't put it around on one side. Since they're sharing the central atom, they still kind of want to be symmetric, if at all possible. Okay, obviously they're not going to be perfect. Okay, and then let me put my hydrogen electrons here. Now hydrogen can only have single bonds, because remember, he only has a maximum of 2. He actually only has 1 gap here. He doesn't have gaps around the rest of them because that first period only has 2 electrons for the max. So draw in your single bonds. And now we gotta see what's left. We can't leave it like this, or it's CH2 and another CH2. Our carbon and our carbon, our central atoms, still also have to be bonded together. So I could leave it like this, but that's breaking 2 rules. It's leaving an electron alone and by itself, which he prefers not to do. And if I look at this carbon, 2, 4, 6, 7. 2, 4, 6, 7. He does not meet that octet rule. So I'm going to draw a second one around. And now let's do a double check. Hydrogen, 1 valence. 1, 1, 1. Carbon, 1, 2, 3, 4. Carbon, 1, 2, 3, 4. So they meet the valence rules. Now let's check the octet. Hydrogen, single bond. That's 2, 2, 2, 2. They have a maximum of 2, so we're good. This carbon, 2, 4, 6, 8. Good. This carbon, 2, 4, 6, 8. So let me rewrite. And I have no extra electrons in this case. C double bonds with C, and there are 4 single bonds to the hydrogens. P2, phosphorus, group 15, so 5 valence electrons. Okay, in this case, it's kind of like 2 central atoms again, okay, because there's only the 2 guys there. So I start with a single bond. Okay, are they happy? No, because 2, 4, 5, 6, they're not meeting that octet rule. So now, are they happy? 2, 3, 4, 5, 6, 7. Nope, not happy. Plus, they have a lone electron all out there without a partner. He wants to be in a bond or with a partner, if at all possible. Okay, and so now that guy. 2, 4, 6, 7, 8. 2, 4, 6, 7, 8. So now they are happy. So P has a triple bond with P, and it has 1 unbonded pair of electrons. Okay, last guy, sulfur dioxide, SO2. Sulfur has 6, 1, 2, 3, 4, 5, 6. Oxygen, 1, 2, 3, 4, 5, 6. Oh, what do I do there? They both have 2 gaps. They both have 2 gaps. Okay, and so in that case, I'm going to go with the least electronegative, which is sulfur. If we haven't gone over electronegativity in your class yet, then just think about the fact that we want balance. So sulfur would be the best one to be in the center so that we have some symmetry with the oxygens on the outside. But the actual rule is least electronegative. Okay, I'm going to draw in those dots. And remember, it doesn't matter what you're drawing in as long as you're showing something so I can see the process, so I can see what electrons are bonding with what. Okay, and we know they're at least going to have single bonds, so I always start with a single bond because I know they have to have at least that to form what they need. And then I check and see, are they happy? 2, 4, 5, 6, 7. Nope. 2, 3, 4, 5, 6, 7, 8, 9. Oh, this guy's all mixed up, huh? So this guy in sulfur is actually going to break the octet rule. Okay, because I want to make those oxygens happy. Okay, so let's see if I can get him back into place, because I can know the oxygens can have a double bond. 2, 4, 5, 6, 7, 8. 2, 4, 5, 6, 7, 8. Okay, so now my oxygens are happy. They're all happy with valence electrons. Just sulfur is kind of out of whack here. 2, 4, 6, 8, 9, 10. 1, 2, 3, 4. I think I have 1 extra electron drawn there. Let's just get that. 1, 2, 3, 4, 5, 6. Yeah, I have an extra electron. Okay, so sulfur in this case has 2 extra dots. Oxygen still has those 2 unbounded pairs of electrons. Oxygen's happy. 1, 2, 3, 4, 5, 6. 2, 4, 6, 8. Oxygen's happy. 1, 2, 3, 4, 5, 6, 7, 8. 2, 4, 6, 8. Sulfur just breaks that octet rule. 2, 4, 6, 8, 9, 10. And that is because he steals from the D block. Okay, and if you're in general, you won't be tested on the sulfur dioxide ones. All of yours will meet the octet rule and the valence rule. And that's it.